Hello and welcome to our last lecture of Physics 101. In part 2 of chapter 16's lecture, we'll look at musical instruments, speech, and hearing. Let's start by talking about how musical instruments work with regards to the physics of standing waves. We learned in the last part of this lecture, in part 1, that standing waves are produced whenever waves are confined to a medium, basically, that holds the waves inside. So, for example, we looked at a string tied on both ends, so it was fixed, so the waves had to bounce back and forth. And remember that these waves that bounce back and forth then interfere with each other and produce standing waves. So musical instruments are based on this, whether it's a woodwind or a brass or even a string instrument, they all are based on this principle of standing waves. If we think about woodwind instruments like flutes, saxophones, clarinets, and so forth, the tubes where the sound is produced in these tubes will only allow standing waves, which remember is constructive interference, at certain frequencies or wavelengths that are related to the tube length. All other frequencies result in destructive interference, meaning no sound. So for a flute, it's open on this end where the musician blows air into it, and it's also open on the far end here where the sound leaves. So this is called technically an open tube. It's open on both ends. And these are the first three modes of standing waves that are produced for an open tube. And this is the mathematics here, the equations for the wavelength, 2L over M, where L is the tube length, M is the mode number, so this is M equal 1, M equal 2, M equal 3, and so forth. And then these are the frequencies that are allowed for this particular tube geometry. Again, the frequencies are based on the length of the tube there and the mode number. So in order to demonstrate this effect, let's watch a couple of videos that I made. One with creating sound in a tube using a speaker, and another shorter one where I actually whistle into a tube. Hi, I'm here again in my lab, and I want to demonstrate to you standing sound waves inside of a tube. So this is a little speaker. It's a little loudspeaker, and I've got it connected again to a signal generator back here where I can adjust the frequency by turning this knob. So you can listen to the different pitch. As I increase the frequency, you can hear the pitch of the speaker increase. And one thing you notice is that as I increase the frequency, the loudness of the sound is pretty much constant. In other words, the sound doesn't get loud or soft at particular frequencies. So what I'm going to do is, let me go down here to back down to a low frequency. I'm going to connect this speaker here to the end of this cardboard tube. And so I'm going to do this by clipping it right here, like this. And now you can see that the tube here is pretty long. It goes all the way across the desk to the other side. In fact, it's 1.87 meters in length. So it's about 6.5 feet long, almost 2 meters in length. And what I did is I did some of the calculations, like the ones shown in the lecture notes, to figure out what are the frequencies that will produce standing waves in the tube. Now remember, standing waves are called modes, and each mode represents a harmonic frequency, and you can think of it as when the frequency is in resonance with the tube. So at these, and basically that's constructive interference. That's what we have going on here. So what we predict here is that according to the calculations here, every 90 hertz, we should hear a mode or a harmonic frequency or resonance or constructive interference, whatever you want to call it. Meaning, every 90 hertz, we should hear the sound get louder. And in between those loud sounds, we should hear the sound get softer. So let's go ahead and do this experiment. So I'm going to start here at We'll start here at the first loud tone, which is right here at about 410 hertz. So this is relatively loud, what you're hearing right now. Now, if I go up to 460, the sound is much softer. In fact, you can barely hear it now, right? Because this is destructive interference inside the tube. Now, remember our first mode was at 410, so if I add 90 hertz to that, we should get a loud tone at 500. So this is, again, this is 460, 470, 80, 90, and here's 500. Notice it's loud again. Let's keep going up. 540, halfway in between the louds now, is going to be soft again. You can barely hear it. From 500, we expect to hear another loud tone at 590, which is right here. So relatively loud again. Keep going up. 640, soft. Let's go up to 680, which should be the next loud. Right here, loud, soft, and our next loud we expect at 770, right there, soft. Here's 860, our next loud one. This one maybe not quite as obvious. And we can just keep going. We get soft, and then here's 950. This one shows up really nicely. So again, we're just going up by 90 hertz every step to get to different modes of vibration. Let's just do two more. We'll go up to, here's at 1,000, relatively soft, and our last one should be at around 1,040. Right there, loud again. So here's a little interesting demo that you can actually do at home. If you get a piece of tubing, now you can use, for example, a paper towel, empty paper towel cardboard tube. It'll work just as well. This is a piece of plastic PVC pipe from the garage. And if you, what I'm going to do here is I'm going to whistle into the tube, and the tube is going to only allow certain frequencies or pitches to be played or heard. And so it's kind of a strange phenomena here. So for example, if I whistle without the tube, I can whistle from low to high to low, and it's a continuous spectrum of pitches or sounds. So watch, listen to this. All right, so you heard it go up smoothly and then back down smoothly. Now watch what happens when I try to do that into the tube. This time you could hear it going up in steps. Now why is that? Well, because the tube only allows certain frequencies to resonate inside with constructive interference. These are the standing waves that we talked about in the lecture that represent different modes of vibration for the sound waves inside of this tube. So instead of allowing every different sound or pitch to be played, the tube only selects those frequencies that have to do, with the correct geometry of the sound waves fitting inside the tube. So listen again as it steps up in discrete frequencies. By the way, this is the way musical instruments work, right? Musical instruments, the geometry of the instrument actually only allows certain tones or pitches to be heard. And, with a musical instrument like a flute or clarinet or something like that, there are holes placed along the tube of the instrument, and the musician can lift up fingers and open up those holes to effectively change the length of the instrument, which will allow different pitches or different musical notes to be heard. Brass instruments basically work on the same principle as the woodwind instruments. The only difference here is that with a brass instrument, the musician, his or her mouth is actually closed here when blowing air in there. The lips are close together. So this, and then of course the bell of the instrument here is open. So this is called an open-closed tube. And the geometry of the standing waves are a little bit different because one end is open here and the other is closed. And so, you know, an open end, it turns out, creates a node, and closed end creates an antinode. So the geometry of the wave patterns is just a little bit different. Here are the results again for the allowed wavelengths and frequencies of this particular open-closed system, and again, the musician is creating vibrations with their mouth at this end, and then the instrument itself is allowing certain pitches to come out and produce sounds, which corresponds to specific musical notes. String instruments, these would be guitars, harp, piano, violin, etc. We talked about the standing waves on the string in part 1 of this video, and we saw, these similar patterns here for vibrations, the different modes of vibration, the fundamental vibration, or this is the first harmonic, it's sometimes called, or this is the fundamental frequency of vibration. But then we can have other modes where the frequency is doubled, and these are called the harmonics, or overtones, they're also called in music. So one thing that's important about all these different harmonics and overtones is that they determine the what is called the musical tone quality, or the timbre of the music. So to see what this means, for example, suppose this guy plays a middle C, which is 262 hertz. He plays it on his acoustic guitar here, and the flautist here also plays a middle C, and the trumpet player here plays the same note, middle C. Well, they're all playing the same note on the musical scale, but obviously they all sound very different. Now, why is that? Well, it's because they all have a different tone, and the tone is due to the presence of the higher harmonic frequencies. So this is called a frequency spectrum, and this is a frequency spectrum of a guitar. So what the frequency spectrum tells us, this is frequency down here in hertz, and the vertical scale tells us the intensity of the particular frequency. So this, if they're all playing, remember, a middle C, 262 hertz. So notice this peak right here is right at 262 hertz. This is the fundamental frequency of this spectrum, and it determines the pitch that we hear. So the pitch is middle C. However, notice there are harmonic frequencies present also, and harmonics are just multiples of the fundamental frequency. So this one here is 2 times 262, which is 524. This one here is 3 times 262, which is 768. This one is 4 times 262, which is 1048, and etc. So notice that all of these upper frequencies here correspond to harmonics, and we hear all of this stuff blended together, and these harmonics determine the tone quality of the instrument. This is what makes a guitar sound different from a flute, which sounds different from a trumpet. These are some harmonic spectrums for various instruments. So here is a pan flute, and if you've ever heard pan flute played, they're common in South America, indigenous cultures. Beautiful music, and the reason it sounds so nice to our ears is look at the spectrum. The spectrum is absolutely clean. It only has the fundamental frequency here, so we call this a pure tone. There are no harmonics or upper frequencies here that sort of distort the sound. And so that's what gives the pan flute a real pure and sort of soothing sound. Now, a trumpet is kind of on the opposite end of the spectrum. The trumpet has a real sort of glaring, brash, sound with a lot of energy. You know, it can be played loud in jazz music and so forth. And what makes the trumpet unique is look at all these harmonic frequencies here. So here's the fundamental frequency, but notice the harmonics, some of them are higher than the fundamental. And so added together, all of these give the trumpet its unique sound. And we will actually be making, or at least attempting, to synthesize the sound of the trumpet next. So let's go ahead and watch a video here on how we can try to make our own version of a trumpet sound. This is a sound synthesis tool that's online, and it will play different harmonics of a sound. So for example, let me hit the sound switch here. So what we're hearing here is a single tone right here, and this is the graph shown here. Now I can add the first harmonic, which is twice the frequency, and likewise I can add the next harmonic, which is 3 times the original frequency, and keep adding these. So what I'm going to do here is instead of just playing a single tone, which doesn't sound like a trumpet at all, for example, let me just play this one here. That one's a little high. Let me try another one. There we go. So that doesn't really sound like a trumpet because it's only a single harmonic. It doesn't have all of the harmonic components which give us the tone or timbre of the trumpet. So what I'm going to do is I'm going to, let me turn off the sound here. I'm going to add all the components together to try to match the spectrum of the trumpet based on the graph shown in the slides. So I'm just entering manually how much weight I give each of these frequency components here to each harmonic. And there's just a couple more I'm going to do here. 0.19, and last one here, 0.07. Okay, so this spectrum here that I've basically created is a fairly decent match to the one that you'll see in the lecture notes. So let's listen and see what this sounds like now. So this sounds a lot like a trumpet to me, right? So this is how musical synthesizers work to create the sounds of different instruments. They just basically match, and they do it, you know, a little bit more sophisticated than what I'm doing here, but they basically create a spectrum that matches the instrument that it's trying to mimic. In this case, we did our best to mimic a trumpet, and we got something that I think sounds, you know, fairly close to a trumpet. Let's listen to it one more time. The last topic of our course here, we're just going to briefly introduce some of the concepts in physics of speech and hearing. So as you know, human speech is produced by our vocal cords. The vocal cords are membranes inside your larynx or voice box that vibrate and produce sound when air passes through them. And we can adjust the tension in our vocal cords to adjust or vary the pitch of our voices, whether we're singing or talking. So let's go ahead and we'll watch a video to see vocal cords in action. It's really quite fascinating to see vocal cords and what they do, how they vibrate during speech and singing.
Whenever you're ready. High pitch. Low pitch. Middle pitch, very soft. Good, a little louder. Louder still. And again now. Good, now say hee hee hee. Nice loud he. And again. Once more. Try a real high pitch. Now give me a singing. At a low pitch and then sing up. Okay, can you go any further? Okay, good. And now high to low. All right, say he, he, he.
So the vocal cords make sounds, but how do we actually speak and produce words? Well, the trick here is through something called formants, or vocal resonances. So the shape of our mouth and tongue during speech produces standing wave resonant frequencies, allowing certain harmonics to dominate. So these formants are acoustic resonances within the voice box that produce spectral peaks in the frequency spectrum of the voice. So to see what this means, let's take a look at the cross-section of a human head. So the vocal cords are down here, of course, in our throat. This is our windpipe that goes down to our lungs. So as we, exhale, we can make our vocal cords vibrate and produce sounds. All right, but the vocal cord spectrum is basically just a continuous spectrum of all frequencies. But though that sound has to come up here and travel through our mouth cavity and our nasal cavity. So these cavities act just like a musical instrument does. By changing the shape of our mouth and using our tongue and so forth, we can create resonances at different frequencies. And so these are the voice cavity resonances. Wherever you see these peaks, that's where certain frequencies are going to be heard more loudly. So when we combine these resonances with the output of the vocal cords, we get the resulting spectrum of speech. And again, we can vary this by, we can produce different sounds with our mouth and tongue by changing the location of these peaks or formants. So the formants produce the various speech sounds. Let's look at some examples here. So this is, remember that what a formant is an acoustic resonance within the voice box that produces a spectral peak in the frequency spectrum of the voice. So look at, this is the shape of the mouth and tongue when we sound out the vowel E. So when we make a sound like E, notice we see three dominant formants here. We see a peak here at low frequency, but we see these two peaks here at high frequency. Compare that to a sound like ooh. All right, we can say ooh, and ooh has no high frequency components. They're completely gone. And this is why the sound ooh is a little more soothing than the sound E, like the sound that we might make when we scream. It all has to do with where these frequency components are in the spectrum of the sound being produced. And these are changed, of course, by the way we talk, by the way we use our mouth and tongue to produce all the different vowels. I just want to real briefly mention regarding hearing. We're not going to go into any detail here, but the ear canal, here's our outer ear here, here's our ear canal, here's the eardrum that actually vibrates to detect sound waves, and it's connected to some tiny little bones, the anvil and stirrup bones, and those in turn are connected to auditory nerves that basically, go to our brain, and our brain interprets those vibrations as sound. But the thing we're going to focus on here is this ear canal here, which is about 1 inch long. Basically is an open closed tube, similar to a musical instrument like we were talking about. So the sounds that enter the ear actually will have resonances at certain frequencies, and those sounds will appear louder. So our hearing, interestingly, is not, in particular, it's not uniform across the whole sound spectrum. There are certain frequencies that will sound louder than others, and this will, vary from individual to individual depending on their age and also the size or depth of their ear canal. They will have resonances at certain frequencies, and you might hear those sounds a little bit louder. All right, the last thing we're going to do here is just a fun little demo that you can have fun with at home. We'll watch the video on the tone matrix. And that is it then for our lecture on the course. I've had a lot of fun doing these lectures for you, and I hope you enjoyed them, and I hope you learned from them. Take care. This is called a tone matrix. This grid of squares represents different pitches. As you go up higher, it'll be a higher pitch or a higher note, and going to the right is time, and so it's going to sweep across. So for example, if I want to add a chord down here, I can add these 3 notes, and it'll play this chord. Let's add another chord right here. And we'll do another one over here. And we can just, let's add a couple more chords there before we add our melody. Okay, so now we've got the chords going, so it's sweeping across and playing those chords. Let's add some melody here. And you get the picture. You'll have fun playing with this. Here's the URL up there if you want to play with this on your own computer. Have fun.